Now I'm gonna be explaining a very important article that uses contrastive learning for few-shot learning, and of course for the application of remote sensing. So I'm gonna be explaining this paper in 2023. Classifying and segmenting patterns from a limited number of examples is a significant challenge in remote sensing and Earth observation due to difficulty in acquiring accurate labeled data in large quantities. Previous studies have shown that meta-learning, which involves episodic training and querying support sets, is a promising approach. However, there has been little attention paid to direct fine-tuning techniques. So this paper repurposes contrastive learning as a pre-training method for few-shot learning for classification and semantic segmentation tasks. Specifically, we introduce a generator-based contrastive learning framework, which is called GenCo model, that pre-trains backbones and simultaneously explores variants of feature samples. In fine-tuning, the auxiliary generator can be used to enrich limited labeled data samples in feature space. We demonstrate the effectiveness of our method in improving few-shot learning performance in two key remote sensing datasets: this agriculture vision datasets and Eurosat dataset. So this is the illustration of pre-training stage. In the pre-training stage, we follow the training strategy of contrastive learning to train the backbones and projector jointly with abundant unlabeled images. So an additional feature vector Q prime, this one is added by passing the real feature Q, this is a real feature, and a noise. So we add noise, and it's a generator to the generator, and the generator is trained end to end with the contrastive learning framework. So in the first stage, we pre-train different backbones with contrastive learning models on unlabeled data. To be more specific, there are roughly 1,300,000 images with this shape, and these images are randomly cropped from the raw images, and we use all these unlabeled images as input to pre-trained backbones without any supervision. So it's very cheap. After the pre-training, we move to the second stage, which fine-tunes the pre-trained backbones for the downstream few-shot task. Since the proposed contrastive learning is unsupervised, there is no information on any base classes, unlike the usual setting for few-shot learning. Only case samples are provided for fine-tuning during the evaluation. And the evaluation will include both base and novel classes based on different downstream tasks to optimize the classification accuracy of agricultural patterns. So in every training iteration, a training sample X is augmented into different views named query in the key, and these views contain the same semantic meaning but also variation introduced from data augmentation. So everything about data augmentation I've explained in the playlist for contrastive network, so I skipped that. And they use info and CE loss for that contrastive loss. And I've explained info and CE several times in the playlist for contrastive networks. So entries, so we design a generator G that takes the query and the random noise. So entries of Z are assumed to follow a normal distribution with mean 0 and variance 0.1. And then we generate a new sample in the feature space using this generator. Because you have a generator, we have a sample and noise, condition on theta. So we get the new sample. Now that we have this new sample, we eventually obtain an additional positive pair, Q prime and K. So this is our positive pairs. But along with the original positive, the framework provides enhanced contrast and improve the quality of embedding during training with an additional little computation. So together, based on positive and negative pairs, and a temperature parameter tau, this is temperature parameter everywhere, it's a hybrid parameter. So this is the architecture for few shot fine-tuning. So our backbone give us features, and then we generate new sample because we have generator, and then we do classifier and segmentation decoder. So with the contrastive learning applied in the first stage, here in the first stage, we freeze the encoder and fine-tune model with few label images. We first create a small balanced training set with K images per class, K shots, and these classes can either be seen or be novel classes. Then each image was encoded into feature space, forming a vector Q with label Y. So while the traditional fine-tuning method applied the feature queue directly to downstream tasks, we take advantage of the generator from the contrastive learning framework to generate labeled samples. The Q prime share the same label with Q, forming an extra label data. So we obtain 2K labeled data points given K images. Then during the fine-tuning, the generator G is differentiable. So we add one fully connected layer to the few backbones without introducing external linearity. We assign randomly initialized weights to add classification layer. In the few-shot semantic segmentation task, we choose the lightweight segmentation model for fine-tuning given limited training samples. Concretely, we add a 5-layer decoder based on the encoders pre-trained from contrastive learning. So we can compare between weights from supervised ImageNet and weights from this dataset, from this model on this dataset for 10-shot classification. And you see the accuracy is improved by 10%, improved from 55 to 65. And for comparison of classification task between the 10-shot and the end-to-end training using the full agriculture vision and ResNet 18, we get slightly better improvement.